Good afternoon. Today we're introducing the American Standard Code for Information Interchange, or ASCII. It's basically a list of numbers that represents each character in the American alphabet, plus a couple of punctuation marks that the Americans think are important. We want to know what we mean by a character set and understand its limitations. We want to understand what it means by a 7-bit ASCII character set, what the limitations of that are. We want to be able to understand how to answer the type of questions that come up in an exam pretty frequently, especially if you're told, for example, capital A is a particular number. Can you work out the number for capital B, etc. Blah-de-blah-de-blah-de-blah, blah-de-blah-de-blah. Don't think we need to understand or remember any of that. The point is, if you are able to transmit binary data via Wi-Fi or a fiber optic cable or via a satellite or whatever, it doesn't really matter, as long as it can be received from one space in the world to another. If people in one country thought a capital A was this binary number and somewhere else people thought a capital A was this number, they're different, and so we're going to get confused. So we have to standardize and say, just like we did in our very first P lesson where we had a binary value for each person in the class, we're going to have a binary value for each letter in the alphabet. And it has to be standardized so that everybody knows which letter is which combination of binary values. That's essentially what ASCII is. ASCII, by convention, uses 7 bits. Why? Well, we can't just have 1 bit because that's enough for either A or B. We can't just have 2 bits because that would be enough for A, B, C or D. We can't just have 3 bits because 2 to the power 3 is 2 times 2 times 2 is 8. We'd be able to have A, B, C, D, E, F, G or H. 4 bits, class charts positive question, how many possible characters could we have? So we talked about 2 to the power 5 is 32, as in 5 bits gives us 32 different patterns, which is enough for the alphabet. So why do we need 7 bits if 5 is enough to give us every letter of the alphabet? So with 7 bits, we've got 128 different possible values. Maximum number would be 127, but 128 different values because we include zeros. How can we calculate that? It's 2 to the power n, where n is the number of bits. 2 to the power 7 means 2 times 2 times 2 times 2 times 2 times 2 times 2. Is that enough? Well, let's have a look. ASCII uses all sorts of weird and wonderful things from the old days of typewriters that we probably don't use anymore. And all of the punctuation that Americans think are important, all of the numbers, all of the capital letters, a few more bits of punctuation, all of the lowercase letters, and even a delete character, all the way up to 127. Is that enough for us in Britain? So if you notice, these pesky Americans are saying that a $sign in ASCII is the hexadecimal value 24 or the decimal value 36, which in binary is this. We can ignore octal, we don't have to do that at GCSE. It just means each value has 8, a base of 8. Look, it goes 0, 1, 2, 3, 4, 5, 6, 7, and instead of going 9, it goes 10. But it's not 10 in denary, it's 10 in octal. But you can ignore octal. They've got a $sign, but they haven't got a Great British pound sign. So as soon as you start putting a pound sign, you can't represent it using ASCII. Are there any other differences? Are there any other limitations, any other characters that you might potentially use at any point that is not represented by ASCII? So the big omission here is any form of internationalized characters. So way before Donald Trump, there was an example of inbuilt institutional racism in America. The American Standardized Code for Information Interchange, if you speak Kanji or Korean or Hebrew, or even if you speak French with an accent, you can't send that data using ASCII. You can still send that data, you just have to use a different encoding scheme other than ASCII, which uses more bits than ASCII does. Okay, enough of me waffling. Let's get started, please. We're going to go through this one together. Your job is to find an ASCII table So it's probably worth just searching for American Standard Code for Information Interchange. Just search for ASCII. And then Control and F on your page to search for the character that you need. I need G. So a lowercase g, it's a picture so I can't search, that's sad. A lowercase g, well I've got a lot to choose from. That's octal, I'll ignore it. That's HTML, I'm not even going to explain it yet. It's hexadecimal, I want this one. Decimal, 103. And you should be able to convert these by hand. We're going to do some practice of that, and then we'll check and see if we've got it right. So 103, we should be able to get binary and hexadecimal. Let's see, shall we? 103. 1, 2, 4, 8, 16, 32, 64, 128. Can I use 128? No, it's too big. Can I use 64? Yes, I'm going to need to use 64. So therefore, to get from 64 up to 103 is 36 to get to 100, another 3 to get to 103, that's 39. I'm going to need 32, so I put a 1 underneath. That leaves 7 left. 16 and 8 are bigger than 7. And then I know that 7 is 4 plus 2 plus 1. That should be binary. 0 2 1s. 2 zeros, 3 1s. Separate them out into nibbles. Once we've separated them out into nibbles, we can convert them to hexadecimal, because each hex character is just 4 bits in binary. So even though previously we did 1, 2, 4, 8, 16, 32, 64, 128, we're going to take this nibble separately, and it's just 7. And we're going to take this nibble separately and pretend it's just now 1, 2, 4 and 8. So we've got a 4 and a 2 is 6. So in hexadecimal, the lowercase letter g is 6, 7. If we've done it right, shall we check? Lowercase g is 6, 7 in hex, 103 in decimal. It doesn't say binary, which is nice because you're going to have to do it yourself. Alright, I'm going to go one more example and then I'll give you time to work through these yourself. Let's do denary. Going from denary to hexadecimal is possible if you know your 16 times table up to 16 times 16. I'm a bit rusty on the 16 times table. So instead, we're going to go to binary first. 57. These are too big. We need 32. So if we've got 32, that's going to be another 25 to get up to 57. Oops, crossed out the wrong number. That was silly. I've got to get 9, which is 8 plus 1. So that's our answer in binary. Your job now is to separate them out into 4-bit nibbles. That's 3 in denary. That's 9 in denary. So in hexadecimal, it's 3, 9. I'm going to give you some time to work your way through. So 39 in hex. Where is it? 3, 9 in hex. I can't say 39, it's not the same thing. 3, 9 in hex, 57 in denary is the ASCII code for 9. Okay, so we're going to go through this one where we start with binary this time. So I'm just going to write this down on my piece of paper before I show it. So 0, 0, 1, 1, 0, 1, 0, 0. That's the binary data that's been received. We can then convert that to both hexadecimal and denary. I'm going to do hexadecimal first because it's easier. 1, 2, 4 and 8. 1, 2, 4 and 8. It's a hexadecimal question. you always write down A, B, C, D, E and F from 10 up to 15. This is 3, that is 4, so we didn't actually need that table, but it's not wasted time because it's useful to help us remember. So in hexadecimal this is 3, 4. So I'm going to write that 3, 4 base 16. What is it in denary? Well, I'll write out the thing all over again. 0, 0, 1, 1, 0, 1, 0, 0, 1, 2, 4, 8, 16, 32, 64, 128. We've got 32 plus 16 plus 4. What's that? 48, 52, if my maths is right. 52 base 10. Then we have a look at the ASCII table and try and find 34 in hexadecimal. Not 34, sorry, 34 in hexadecimal. Should be 52 in denary, decimal. And the ASCII code is a 4. So it's a 4. What did we say it was? 52. Hexadecimal was 3, 2. And does that make sense? Well, yeah, it kind of does, because they're in a logical order. You might have an exam paper that says if a capital letter is 65, so if a capital A is 65, what is the ASCII code for 67? And you've got to work out, okay, 65, 66, 67, that's 2 more along in the alphabet, that's going to be C. So you don't have to remember these, you don't have to know that K is 75, but you have to understand that they're in a logical order. For example, if we knew that a 9 was 57, we could have worked out that 52 was a 4. Give you a few more minutes to work through the rest. So if we move on to activity 2, this is much more like what you might have to do in an exam. So we're told that a capital A is 65. We're told that a lowercase a is 97. There is actually a pattern between lowercase and capital, which we can look at later, see if you can work out whilst I'm talking. Digits start at 48. Now, does that start with a 1 or a 0? It should really start with a 0. Yeah, a 0 is 48. What does that mean? It means capital B is 66, lowercase b is 98, a 1 is 49. And they go in a logical order. You don't need to know anything at all about the punctuation. You don't need to remember these. You'll be told something like this in the exam. So what do we mean here? If a lowercase g is 103, what on earth is m? Well, you might be able to do this in your heads. I probably can't. So I'm going to type out the alphabet. A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P, Q, R, S, T, U, V, W, X, Y, Z. I managed to do it without singing the little song. So if we want to get from G to M, we have to go 1, 2, 3, 4, 5, 6 spaces across. That's what it means from G to M is 6 spaces in the alphabet. 103 plus 6, I hope you would agree, is this. So I want to go from 9 to 4. A little bit easier, but I'm still going to do it. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. I want to go to 4, so that's 1, 2, 3, 4, 5 spaces to the left. From 9 to 4 is, did I say minus 5? Yeah, that makes sense. So we need to work out what this is in denary. If it's 5 earlier in the ASCII character set code, we've just got to take 5 away from this to get 52. I'm not going to do all of them, but we'll do one down here. From, oh, challenging. From F to a capital Y, that's a bit mean. Let's not do that one, shall we? Let's do F to a capital F. Just to, no, let's not. Let's really not. Let's do a lowercase y. No. It looks like quite a lot of them go capitalised and not capitalised. So we probably need to be able to do that, don't we? Okay. What is 97 take away 65? What's 32? What's 32 in binary? It's just 1 0, sorry, 1 1 and lots of zeros, isn't it? So let's do a little thought experiment. Let's say 97 and 65 both in binary. Let's look at the difference. 65 and 97. What have I done with my camera? I've closed it. Oh no, I haven't. There we go. So a capital A and a lowercase a. We're told that a capital A is 65. 1, 2, 4, 8, 16, 32, 64, 128. How do we do 65? Well, that's too big. That's not too big. We need an extra 1 to make 65. Nice. To get a lowercase a, we were told that was 97, which is 65 plus 32. That digit there is a really fast way for a computer to know if something is capitalized. So when you're converting from a capital letter to a lowercase letter, all you're doing is changing that bit. If that bit is set, a 1, it's a lowercase letter. If that bit is not set, a 0, it's a capital letter. It's all a computer is doing. It's just changing the zeros to 1. Okay. So we've got an extension here. We want to write a program that can do all of the hard work for us. The user types in just one letter, converts it to denary, converts it to binary, converts it to hex, and shows them all. So let's ask the question first. We need to ask the question, which letter? There we go. It's rude to ask a question without listening to the answer, so we want to store the answer somewhere. Then we want to say the character and then what the user has typed in. So we're going to concatenate and then the variable. Nice. Then we want to work out what it is in denary. So let's make a variable called denary, and somehow we've got to have a number in there in denary. But we've got to be careful with data types because denary is an integer and we can't concatenate integers and strings. Strings are text, strings of characters all joined together, and an integer is a whole number. If we want to concatenate like this, we've got to convert it to a string first. This is better. But it's not always going to be 65. We want to do the conversion. So we could search for it, but we can't search in the exam. So let's just use the resources that we'll have access to, printed and digital, in the exam. That's the programming language subset, the PLS. And let's search for ASCII. Oh, this looks promising. CHR integer. So if you give it a number, it will work out the character. That's nice, but not very helpful for us. We want to go the other direction. So print CHR 65 should give us a capital A. And if we add 32 to that, it should give us the lowercase number, 97. Yeah, sorry, the lowercase letter. But that's not what I want. I want to go the other direction. Oh, that looks promising. ORD with one parameter, and that parameter is the letter. That's what we want here. So if we type in any old thing, it should tell us what it is. So a B should be 66. And a lowercase b should be 66 plus 32. Yeah, good, it works. I'm going to copy that, try and change it to binary and hex. Let's see. Binary equals, we've got to work that out. And hex, well, got to be careful here. because notice hex goes a different colour. It's a built-in keyword, and you'll see why in a sec. There is a function built into Python called input. There is a function built into Python called ord, and a function built into Python called bin. So let's use the bin one first, shall we? Comment that one out, because we're not quite ready for that. Comment that out. So we have an A. It does convert it to binary, but we have that nasty prefix on the front. We'll ignore that for now. Seems fine. I'm going to call it hexadecimal. That's better. We have these prefixes here just to tell us that that is denary, no prefix. 0b means it's binary, and 0 times means it's hexadecimal. Otherwise we might think that that was, oh gosh, what would that be? 1,000,001. It's not. It's 1,0,0,0. It's in binary. That is not 41. It is 1 plus 4 times 16. Just in the same way that that is 5 plus 6 times 10. So that's your extension. I'm not going to share the code with you, but you can try and write the code and then use your code to help you with all of these tables. So when you've finished all that you can, please save the Word document, upload the Word document to half term 2 data 2.